In this third installment of the NMR Lecture series, I'm going to overview the process that occurs during the collection of an NMR spectrum and then discuss the instrument components that are needed to collect an NMR. As we look at what happens during the process of an NMR spectrum collection, we are going to be doing this with the perspective of three different sort of signals. The first thing we're going to look at is the perspective of B naught, the external magnetic field. And then we're going to look at the signal along the z-axis and the magnetic signal along the x-axis. So we're going to be looking at what happens along all three of those areas, and we're going to be thinking about it with perspective of time along the y-axis. So the first thing that happens is we have our sample, and it's not in any sort of magnetic field. And so we have the spins in our sample just randomly oriented, and there's no net magnetic spin. The spins just sort of cancel themselves out. We're going to call this state A. While state A exists, there is no external magnetic field, and that would mean there is no magnetic field along either the z or the x-axis. What's going to happen then is we're going to turn on the external magnetic field. So that's going to get turned on, and then our sample will be exposed to the external magnetic field, and we know that our spins will either line up with or against the external magnetic field. A few more spins will line up with the magnetic field than against the magnetic field, and so we end up developing a net magnetic field along the z direction, m sub z. Right, so when that external magnetic field is turned on, what you're going to see if we were looking at the magnetic signal along the z-axis is that as those spins started to line up, we would see a gradual increase in the signal strength along the z-axis. And that would, of course, represent the formation of that net magnetic field of our sample. During this time, along the x-axis, there's still no signal. So the x-axis is remaining flat. That is the point when we are going to apply our pulse of electromagnetic radiation. And this pulse of electromagnetic radiation is what causes m sub z, the net magnetic component of your sample, to flip into the x-axis. So we're going to see when that arrow, that m sub z, flips down into the xy plane, we're going to see a sudden drop in the magnetic field being detected along the z-axis, and a sudden increase in the magnetic field being experienced along the z-axis, or x-axis rather. So the z-axis drops, the x-axis increases, and B naught is still on. It's not changing. It's just going to be up there and on. Okay, so what happens here, and I'm going to call this point C in our diagram here. So this would be A, this region. B would be this region here, and that would apply all the way through all three of these. C would be what happens when we apply that pulse. And so when we apply that pulse, this is our z-axis, x and y, x and y. So the before the pulse, your signal looks like this. after the pulse, your signal is down there along the x-axis. And remember that this arrow is spinning. It's spinning around the z-axis. And when it's spinning around the z-axis and pointing at the z-axis, we don't really see anything. But when it tips and it continues to spin, now it spins in, a much greater radius here as it spins around the z-axis, but in the xy plane. And we only applied a pulse, so our arrow will gradually make its way back up to being lined up with the z-axis as it spins around. And so what we're going to see here is this signal around x is going to gradually decrease, and our signal around z is going to gradually increase back up. And of course, this component here, the signal along the the signal along the x-axis is what we know as a free induction decay or FID signal. This is a time-based signal, which is then converted into a wave number-based signal to get the NMR spectrum that we're used to seeing. The FID will have many different time relaxations to it, depending on how many different nuclei types there are, how many different environments. And the details of that were in part 2 of the video. Okay, so now that we've reviewed the process that occurs in the NMR experiment, or the duration of collecting an NMR spectrum, let's take a look at what kind of instrument components we need. In this diagram here, I'm going to point out the important components and discuss them a little bit. Unlike some of the other spectroscopies where we got into a lot more detail about how each of these components works, we're not going to get into that much. We're just going to kind of learn what the components are and not necessarily how much they work, how each component works specifically, but we're going to kind of understand how they all work together to produce what we're used to seeing as an NMR spectrum. So the first component that I want to point out is right here, number 1, and it is a large magnet. This large magnet is, you can see the north and south ends there. This is what's used to create B0, the external magnetic field. The sample is then surrounded by what I'm going to call part 2, which is a transmitter-receiver coil. So this both transmits signals and measures or receives signals, this coil that goes around your sample. And of course, I hope my drawing isn't that horrible that you can't recognize that this would be that NMR tube that we're used to seeing, that glass tube. So this coil would kind of go around that region. And there's much more to this that I don't have drawn, but you guys know that tube is spinning at a really high rate. And that spinning is done to ensure that the entire sample feels a consistent external magnetic field. All right, the next component that we have is part 3, which is the frequency synthesizer. Down here, the frequency synthesizer. This generates radio frequency electromagnetic radiation. Okay, so as I mentioned in the very first video, NMR works using the radio wave region of electromagnetic radiation, and then it uses the magnetic component of it. So this instrument component down here will be what generates the electromagnetic radiation. That's going to pass through a pulse switch and power amplifier. What this does is it converts the radio frequency generated by the frequency synthesizer into an intense pulse of radiation. So it converts the generated electromagnetic radiation into an intense pulse of radiation, which is then passed through into the radio frequency transmitter, which is simply what transmits it up to the sample. So then through that coil, the pulse that has been created through the other instrument components is applied to your sample. The same coil then detects the signal along the x-axis, which is passed along to a radio frequency amplifier, something that amplifies the signal. That signal is then passed down along to a phase-sensitive detector. The phase-sensitive detector separates the signal coming from the radio frequency generator, the one here I'm circling in green now, from the signal that's coming out of your sample, the one I'm circling in green now. So there has to be a way for the detector to know which signal is being generated by the instrumentation and which signal is coming from your sample, because they're both running along the same coil. So that phase-sensitive detector does that. And you can also see that the phase-sensitive detector is coupled with the synthesizer and the pulse generator, and it all goes to a computer here. So we need to have all of that connected so that it knows when the pulse is generated and when to start collecting the signal. Here at the time swept computer and FT program, this is going to be where your FID is collected and Fourier transformed into, ta-da, the end product, your NMR spectrum. Once you finally collect the NMR spectrum, usually working on the same computer screen or the same computer program, you will then be able to do things like integrate your peaks. So you can tell, for example, that this one is maybe 2 hydrogens and this one's 3 hydrogens and maybe this one is 1. And you'll be able to usually your sample would contain some sort of TMS peak or something, so you can set your scale and do other manipulations. And then if you so desire, print out or save or transfer into another form to use.